அனைவருக்கும் எங்களுடைய அன்பான வணக்கங்கள். ஒவ்வொரு பகுதியா முன்னேறிட்டு வரோம். எலக்ட்ரோ டைனமிக்ஸ் என்ற தலைப்புல நம்ம இன்னைக்கு பார்க்கக்கூடிய பகுதி வந்து எலக்ட்ரோமேக்னட்டிக்கல் இண்டக்ஷன். நல்லா கவனிச்சு பார்த்தா மேக்னடிசம்னா என்னன்னு பார்த்தோம். மேக்னடிசம் உருவாறதுக்கான காரணம் என்னன்னு பார்த்தோம். ஒரு எலக்ட்ரான் ஒரு ஆர்பிட்டால்ல சுத்தி வர்றது, ஒரு எலக்ட்ரான் தன்னைத்தானே சுத்தி வர்றது, ஒரு ஆட்டம்ல இந்த எலக்ட்ரான் சுற்றுக்கள் எல்லாம் செல் ஸ்பின், ஆர்பிட்டல் ஸ்பின் எல்லாம் ஒரு டொமைனா சிறு சிறு காந்தமாக மாறி வலுப்படுத்தி ஒரு மேக்னெட்டிக் மெட்டீரியல்ல ஃபெரோ மேக்னெட்டா மாத்துறது, மேக்னடைசிங் ஃபீல்ட்ல அது மேக்னடிசம் பெறுறது, இதெல்லாம் பார்க்கிறப்போ கரண்ட்டுக்கும் மேக்னடிசத்துக்கும் தொடர்பு இருக்கிறதா பார்க்கிறோம். ஆஸ்டட் என்பவர் வந்து மூவிங் சார்ஜஸ் பத்தி சொல்றப்போ மிக தெளிவா ப்ரூவ் பண்ணாரு. ஒரு சார்ஜை சுத்தி மேக்னடிசம் இல்லை, ஆனா அந்த சார்ஜ் நகர்ந்தா வரக்கூடிய கரண்ட்டை சுத்தி மேக்னெட்டிக் ஃபீல்டு இருக்கு அப்படின்னு பார்த்தார். ஒரு சார்ஜ் இருந்தா சார்ஜை சுத்தி எலக்ட்ரிக் ஃபீல்டு இருக்கிற மாதிரி நகர்ற சார்ஜ்னால வரக்கூடிய கரண்ட் அதுக்கு பர்பெண்டிகுலரா மேக்னெட்டிக் ஃபீல்டு இருக்கு அப்படின்னு சொன்னார். இப்போ இதுக்கு தலைகீழான ஒரு ஆராய்ச்சி. அப்ப நகர்ற மேக்னெட்டிக் ஃபீல்டுனால ஒரு கரண்ட்டை ஏற்படுத்த முடியுமா? இதான் இந்த சாப்டர் பதில் சொல்ல. அப்போ எலக்ட்ரிசிட்டிக்கும் மேக்னடிசத்துக்கும் இடையே இருக்கக்கூடிய தொடர்புகளை பற்றி 3 சாப்டரா பார்க்கணும். மேக்னடிசம்னா என்ன, மூவிங் சார்ஜஸ்னால ப்ரொடியூஸ் ஆகக்கூடிய மேக்னடிசம், கரண்ட், எலக்ட்ரிசிட்டி, இது 3த்துக்கு அப்புறம் இப்ப என்ன பார்க்கணும்னா எலக்ட்ரோமேக்னெட்டிக் இண்டக்ஷன். இதுல மூவிங் சார்ஜஸ்னால கரண்ட்னால மேக்னெட்டிக் ஃபீல்ட், இதனுடைய கான்வர்ஸ் பொருந்துமா பொருந்தாதா? ஒரு மூவிங் மேக்னெட்னால கரண்ட்டை ப்ரொடியூஸ் பண்ண முடியுமா? அப்போ எலக்ட்ரிசிட்டிக்கும் மேக்னடிசத்துக்கும் உள்ள தொடர்புகள் என்ன அப்படின்றத பத்தி இந்த சாப்டர் பார்க்க போறோம். இப்போ மைக்கேல் ஃபாரடே அப்படின்றவர் ஒரு எக்ஸ்பெரிமெண்ட் செஞ்சார். அவர் என்ன செஞ்சார்னாக்க, ஒரு க்ளோஸ்டு காயில்ல அந்த காயிலோடு சம்பந்தப்பட்ட மேக்னெட்டிக் ஃபீல்டு மாறுச்சுன்னா மாறுற மேக்னெட்டிக் ஃபீல்டுனால ஒரு இன்டியூஸ்டு இஎம்எஃப் ப்ரொடியூஸ் ஆகும், கரண்ட் ப்ரொடியூஸ் ஆகும் அப்படின்னு அவரு ப்ரூவ் பண்ணார். இந்த ஃபாரடே எக்ஸ்பெரிமெண்ட்ல ஒரு சர்க்குலர் அயன் காயில் ஒரு பக்கம் மேக்னெட்டிக் காம்பஸ் க்ளோஸ் லூப்ல கனெக்ட் ஆயிருக்கு, இன்னொரு பக்கம் பேட்டரியோட ஒரு கரண்ட் காயில் கனெக்ட் ஆயிருக்கு. இந்த கரண்ட் காயில்ல ஸ்டெடி கரண்ட் போனா எந்த விதமான விளைவுகள் இல்லை. ஆனா சர்க்கியூட்டை ஸ்டார்ட் பண்றப்பையும் சர்க்கியூட்டை பிரேக் பண்றப்பையும் இந்த காம்பஸ் இடையில ஒரு டிஃப்ளெக்ஷன் இருக்கிறத ஃபாரடே அப்சர்வ் பண்றாரு. இந்த ஃபாரடே எக்ஸ்பெரிமெண்ட் என்ன கன்ஃபார்ம் பண்ணுதுனாக்க, ஸ்டெடி கரண்ட்னால ப்ரொடியூஸ் ஆகக்கூடிய ஸ்டெடி மேக்னெட்டிக் ஃபீல்டுனால ஒரு இஎம்எஃப் ப்ரொடியூஸ் ஆகுது இல்லை, ஆனா இந்த மேக்னெட்டிக் ஃபீல்டு சேஞ்ச் ஆச்சுன்னா ஒரு இஎம்எஃப் ப்ரொடியூஸ் ஆகுது அப்படின்னு ஃபாரடே ப்ரூவ் பண்றாரு. அப்போ ஒரு காயில், அதனுடைய முனைகள் ஒரு கால்வனாமீட்டர் இணைக்கப்பட்டிருக்கு, சர்க்கியூட்ல எந்த இடத்துலயும் பேட்டரி இல்லை. இந்த காயிலுக்கு பக்கத்துல ஒரு நார்த் சவுத் மேக்னெட்டை, ஒரு பார் மேக்னெட்டை இடமிருந்து வலப்புறமாக நகர்த்திட்டு போனோம்னா இந்த கால்வனாமீட்டர் டிஃப்ளெக்ஷன் இருக்கு. வலமிருந்து இடமா நகர்த்தினா டிஃப்ளெக்ஷன் இருக்கு, வேகமா நகர்த்தினா டிஃப்ளெக்ஷன் இருக்கு, நகர்த்துறதை நிறுத்திட்டா டிஃப்ளெக்ஷன் நின்று போயிருது. இது ஒரு டைப் ஆஃப் எக்ஸ்பெரிமெண்ட். காயில் அண்ட் மேக்னெட்டிக் எக்ஸ்பெரிமெண்ட் சொல்றோம். ஒரு காயில் எண்டு கால்வனாமீட்டரோட க்ளோஸ் ஆயிருக்கு, ஒரு பார் மேக்னெட்டை நார்த் போல் வந்து காயில நோக்கி இருக்கிற மாதிரி வச்சு காயில நோக்கி பார் மேக்னெட்டை நகர்த்தினா கால்வனாமீட்டர்ல டிஃப்ளெக்ஷன் வருது, வேகமா நகர்த்தினா டிஃப்ளெக்ஷன் கூடுது. மேக்னெட்டை காயில விட்டு வெளியில நகர்த்தினா டிஃப்ளெக்ஷன் மாறுது. அத போல மாத்தி நார்த் போலுக்கு பதிலா சவுத் போல் வச்சாலும் இந்த டிஃப்ளெக்ஷன்ல கரண்ட் டிடெக்ட் பண்ணக்கூடிய டைரக்ஷன்ல சேஞ்ச் இருக்கிறத பார்க்கிறோம். ரெண்டாவது காயில் எக்ஸ்பெரிமெண்ட். இதான் சொன்னோம். ஒரு காயில்ல பேட்டரி இல்ல, கால்வனாமீட்டர் இருக்கு, ஒரு காயில்ல பேட்டரி கீ இருக்கு. இந்த முதல் காயில்ல கரண்ட்டை ஆன் பண்றப்பையும் ஆஃப் பண்றப்பையும் ரெண்டாவது காயில் மிக நெருக்கமா இருக்கிறப்போ ரெண்டு காயிலுக்கு நடுவுல மேக்னெட்டிக் ஃபீல்டால தொடர்பு இருக்கிறப்போ ரெண்டாவது காயில்ல ஒரு இண்டக்ஷனால ஒரு கரண்ட் தூண்டப்படுறத ஃபாரடே எலக்ட்ரோ மேக்னெட்டிக் இண்டக்ஷன் பேர் சொல்றாரு. இந்த எலக்ட்ரோ மேக்னெட்டிக் இண்டக்ஷன்ல 3 சோதனைகள். ஒரு காயிலுடைய முனையல்ல ஒரு கால்வனாமீட்டர், அதை நோக்கிய ஒரு சட்ட காந்தத்தினுடைய மூமெண்ட், ஒரு பார் மேக்னெட்டுடைய மூமெண்ட். நார்த் போல் காயில நோக்கி இருக்கிறப்ப மூமெண்ட், சவுத் போல் காயில நோக்கி இருக்கிறப்ப மூமெண்ட், காயில நோக்கி வேகமா நகர்றப்ப ஒரு மூமெண்ட், காயில விட்டு வெளியில போறப்ப உள்ள மூமெண்ட், இதெல்லாம் கம்பேர் பண்ணாக்க இந்த மேக்னெட் நகர மேக்னெட் முன்னையும் பின்னையும் நகர கால்வனாமீட்டர்ல வரக்கூடிய டிஃப்ளெக்ஷனை எலக்ட்ரோ மேக்னெட்டிக் இண்டக்ஷனுடைய முதல் வகையான எக்ஸ்பெரிமெண்ட் கன்ஃபார்ம் பண்ணும். ரெண்டாவது எக்ஸ்பெரிமெண்ட், 2 காயில், ஒரு காயில்ல ஸ்டெடி கரண்ட் இருக்கு. அந்த ஸ்டெடி கரண்ட் இருக்கக்கூடிய காயிலை நோக்கி ஒரு மூடப்பட்ட ஒரு சுற்று, க்ளோஸ்டு காயில், கால்வனாமீட்டர் க்ளோஸ் காயில், பக்கத்துல கொண்டு வரோம், கூட கொண்டு போறோம், தள்ளி கொண்டு போறோம், பக்கத்துல தள்ளி மாறி அந்த காயிலை நகர்த்தினா அந்த கால்வனாமீட்டர்ல டிஃப்ளெக்ஷன் இருக்கிறத பார்க்கணும். இந்த க்ளோஸ்டு காயில்ல, பேட்டரி இருக்கக்கூடிய க்ளோஸ்டு காயில்ல கரண்ட்டை க்ளோஸ் பண்றப்பையும் கரண்ட்டை ஓப்பன் அப் பண்றப்பையும் இங்கே டிஃப்ளெக்ஷன் இருக்கிறத பார்க்கணும். இது ரெண்டாவது எக்ஸ்பெரிமெண்ட். இந்த எக்ஸ்பெரிமெண்ட் எல்லாம் என்ன கன்ஃபார்ம் பண்ணுதுனாக்க, ஒரு சுற்றுடன் சம்பந்தமுடைய மேக்னெட்டிக் ஃபீல்டு சேஞ்ச் ஆச்சுன்னா ஒரு எலக்ட்ரோ மேக்னெட்டிக் இண்டக்ஷன் உருவாகும் அப்படின்றத கன்ஃபார்ம் பண்ணுது. இதுதான் ஃபாரடேஸ் எக்ஸ்பெரிமெண்ட் நம்பர் 1ன்னு சொல்றோம். நார்த் போல் காயில நோக்கி இருக்கிற மாதிரி வச்சு மெதுவா வேகமா நிறுத்திடுறோம். என்ன அப்சர்வேஷன் பார்க்கணும். சவுத் போலுக்கும் அதே மாதிரி. இந்த எக்ஸ்பெரிமெண்ட் நம்பர் 1 கன்ஃபார்ம் பண்றது, நார்த் போல் காயில நோக்கி இருந்தா ஒரு டைரக்ஷன்ல கரண்ட்டும், சவுத் போல் காயில நோக்கி இருந்தா ஒரு பக்கத்துல கரண்ட்டும், மாற்றங்கள் வேகமா இருந்தா கரண்டோட மேக்னிடியூட் இன்க்ரீஸ் ஆகிறதையும் கன்ஃபார்ம் பண்ணுது. மூவ்மெண்ட் இல்லைன்னா, when there is no relative movement between the coil and the magnet, there is no electromagnetic induction அப்படின்னு எக்ஸ்பெரிமெண்ட் நம்பர் 1 கன்ஃபார்ம் பண்ணுது. when there is a relative movement between the coil and the magnet, அப்சர்வேஷன்ல இண்டக்ஷன் இருக்கிறத ப்ரூவ் பண்றோம். the induced polarities of the magnetism in the coil depends upon இது மேக்னெட்டுடைய நார்த் போல் சவுத் போல் டிரெக்ஷனை டிபெண்ட் பண்ணிருக்கு. The direction of the current through the galvanometer and the deflection in the galvanometer depends upon which of the magnetic pole moves towards the coil. அப்போ மேக்னெட் காயில நோக்கி நகர்ந்தாலோ காயில் மேக்னெட்டை நோக்கி நகர்ந்தாலோ நார்த் போல் சவுத் போல் டைரக்ஷனை பொறுத்து ஒரு இன்டியூஸ்டு இஎம்எஃப் இந்த மூமெண்ட்ல ப்ரொடியூஸ் ஆகுது. இந்த இன்டியூஸ்டு மூமெண்ட் காயிலுக்கும் மேக்னெட்டுக்கு நடுவுல ரிலேட்டிவ் மூமெண்ட் இருந்தா மட்டும்தான் இருக்கு. அப்போ மேக்னெட்டை பிக்ஸ் பண்ணிட்டோம், காயில மூவ் பண்ணா இந்த நிகழ்ச்சி நடக்குதா? ஆமா நடக்குது. ரெண்டுமே நகர்ந்ததுன்னா இருக்கா? இருக்கு. அப்போ whenever there is a magnetic flux linked with the coil changes, when there is a relative position of the coil and the magnet changes, there is an induced EMF அப்படின்றது ஆப்சர்வேஷன் ப்ரூவ் பண்ணக்கூடிய மிக முக்கியமான உண்மை. அப்போ மேக்னெட்டிக் ஃப்ளக்ஸ் linked with the coil changes related to the position of the coil and the magnet. அப்போ ஒரு சுற்றோட சம்பந்தமுடைய காந்த பாயம் அல்லது மேக்னெட்டிக் ஃப்ளக்ஸ் எப்ப மாறுது அப்படின்னாக்க பொசிஷனை பொறுத்து மாறுது. தள்ளி இருந்தா கம்மியா இருக்கு மேக்னெட்டிக் ஃப்ளக்ஸ், பக்கத்துல வர ஃப்ளக்ஸ் இன்க்ரீஸ் ஆகுது, ஃப்ளக்ஸ் அதிகமா கட் பண்ண இன்டியூஸ்ட் இஎம்எஃப் கூடுது. அப்புறம் இந்த இன்டியூஸ்டு இஎம்எஃப் அப்படின்றது மேக்னெட்டிக் ஃப்ளக்ஸை சார்ந்திருக்கு. மேக்னெட்டிக் ஃப்ளக்ஸ்ன்றது காயிலுடைய ஏரியா ஆஃப் கிராஸ் செக்ஷனையும் மேக்னெட்டிக் ஃப்ளக்ஸை கட் பண்ணக்கூடிய காயிலுடைய கிராஸ் செக்ஷனல் ஏரியாவை டிபெண்ட் பண்ணி இன்டியூஸ்டு இஎம்எஃப் இருக்கிறத ப்ரூவ் பண்ணுது. அப்போ ரெண்டாவது எக்ஸ்பெரிமெண்ட் என்ன சொல்லுதுன்னா, முதல் எக்ஸ்பெரிமெண்ட் மேக்னெட்டுக்கும் காயிலுக்கும் உள்ளது. ரெண்டாவது எக்ஸ்பெரிமெண்ட் ஒரு பேட்டரி கனெக்டட் சர்க்கியூட்டுக்கும் ஒரு பேட்டரி கனெக்ட் ஆகாத ஒரு காயிலுக்கும் நடுவில் இருக்கக்கூடிய அப்சர்வேஷன்ஸ் அண்ட் ரிலேஷன் சொல்லுது. when the primary circuit is closed, கரண்ட் என்ன செய்யுதுன்னா க்ரோ ஆகுது, 0ல இருந்து மேக்சிமம் போகுது. இந்த பீரியட்ல கால்வனாமீட்டர்ல ஆசிலேஷன் பார்க்கும். இந்த காயில்ல மேக்னெட்டிக் ஃப்ளக்ஸ் லிங்க் ஆகிருக்கிறப்போ செகண்டரி காயில், பிரைமரி காயில்ல கரண்ட் ஓடுறப்ப மேக்னெட்டிக் ஃப்ளக்ஸ் உருவாகுது. அது செகண்டரி காயிலோட லிங்க் ஆகிறப்போ செகண்டரி காயில்ல கரண்ட்டை ஸ்டார்ட் பண்ணி 0ல இருந்து மேக்ஸிமம் போறப்போ ஒரு இன்டியூஸ்ட் இஎம்எஃப் பார்க்கணும். ஸ்டெடி ஆகிறப்போ இஎம்எஃப் இல்லை. மறுபடியும் க்ளோஸ் பண்றப்போ மேக்ஸிமம் டு 0 வரப்போ ஒரு டிஃப்ளெக்ஷன் பார்க்கணும். இத ரெண்டாவது எக்ஸ்பெரிமெண்ட் கன்ஃபார்ம் பண்ணுது. When the primary circuit is open, current decreases from maximum value to 0 during the period. Changing current induces changing magnetic field across the primary coil. The changing magnetic flux is linked across the secondary coil and induces a EMF in the secondary coil. Whenever the magnetic flux linked to the coil changes, there is an induced EMF. முதன்மை சுற்றுல சம்பந்தமுடைய காந்தப்பாயம் மாற்றம் செய்யப்படுகின்ற போது அதோடு சம்பந்தமுடைய இரண்டாம் நிலை சுற்றில் இருக்கக்கூடிய கால்வனாமீட்டர்ல மின்சாரம் தூண்டப்படுறத கவனிக்கிறோம். Whenever there is a change in the magnetic field, flux linked with the circuit, an EMF is induced. However, it lasts only so long as the magnetic flux is changing. ஒரு சுற்றுடன் சம்பந்தமுடைய காந்தப்பாயம் மாறுபடுகின்ற போது தூண்டு மின்சாரம் ஏற்படுகின்றது. தூண்டு மின்சாரம் மாற்றம் உள்ள போது மட்டுமே இருக்கு, மாற்றம் இல்லாதப்ப இல்லை. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linked to the circuit. ஒரு சுற்றுடன் சம்பந்தமுடைய காந்தப்பாய மாறுபாடு வீதத்திற்கு இந்த இன்டியூஸ்ட் EMF டைரக்ட்லி ப்ரொபோர்ஷனலா இருக்கு அப்படின்னு சொல்றது ஃபெரடேயினுடைய லா. ரெண்டாவது, இந்த இன்டியூஸ்ட் EMF-னால வரக்கூடிய கரண்டோட டைரக்ஷன், the direction of the induced EMF or the induced current is in such a way to oppose the change that is producing it. Magnetic flux change-னால EMF வருது. இந்த flux change-ஐ induced EMF oppose பண்ணுது. ஒரு இயக்கம் ஏற்படுறப்போ அதுக்கு ஒரு தடை ஏற்படுற போல, ஃப்ரிக்ஷன் ஏற்படுறத போல இந்த மூமெண்ட் ஆஃப் த மேக்னெட்டுக்கு ஒரு ஃப்ரிக்ஷன் ஏற்படுது. அந்த ப்ரூவ் பண்ணக்கூடிய லாக்கு பேரு லென்ஸ் லான்னு பேர். இந்த லென்ஸ் லா, லா ஆஃப் கன்சர்வேஷன் ஆஃப் எனர்ஜிக்கு நிச்சயமாக சப்போர்ட்டிங் ஃபேக்டர். According to the Lenz law, the induced EMF opposes the change that produces it. It is this opposition against which we perform the mechanical work in causing the change in magnetic flux. ஒரு மேக்னெட்டிக் ஃப்ளக்ஸை சேஞ்ச் பண்ண நாம் பண்ண மெக்கானிக்கல் ஒர்க் தான் EMF ப்ரொடியூஸ் ஆயிருக்கு. Therefore, mechanical energy is converted into the electrical energy. Thus, Lenz law is in accordance with the law of conservation of energy. ஒரு காந்தத்தை நகர்த்துறது மூலமா, ஒரு காயில நகர்த்துறது மூலமா, ஒரு கரண்ட் கேரிங் காயில நகர்த்துறது மூலமா அந்த சுற்றோட சம்பந்தமுடைய மேக்னெட்டிக் ஃப்ளக்ஸ் சேஞ்சை நம்ம மெக்கானிக்கல் ஒர்க்னால மாத்துறதுனால நம்ம செஞ்ச வேலை தான் இங்க எலக்ட்ரிக்கல் எனர்ஜியா ப்ரொடியூஸ் ஆயிருக்கு அப்படின்னு லென்ஸ்லா கன்ஃபார்ம் பண்ணதா சொல்றோம். இப்போ ஓவராலா எலக்ட்ரோமேக்னெட்டிக் இண்டக்ஷனை பத்தி நம்ம தெளிவா பார்க்கலாம்.
Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 71. It's on electromagnetic induction, which is the ability of a magnetic field to create current inside a conductor. Now, scientists like Hans Christian Ørsted had already shown that if you have current in a wire like this, it creates a magnetic field, and that magnetic field could affect this compass needle, which is really a small little magnet. And so current can produce magnetic fields. But what scientists like Michael Faraday wondered is, could you take a magnetic field and produce current from it? In other words, was the opposite true? And this is the apparatus that he used to study that. And so we basically have two parts. We have a ring of iron, but on the left side, we have an electromagnet. So you're going to connect this to a battery, and that's going to produce magnetic fields over on the left side. And so the hope is on the right side, that could produce current inside this wire, and then we'd be able to measure that using a galvanometer. And so he set it up like this, and then he closed the switch. And so watch what happens to the current in the wire on the right side as I close that switch. And you can see that we generate a little bit of current, but then it goes away. And this is puzzling. So he opened up the switch and watch what happened. We have a little bit more current, but it's in the opposite direction. So let me kind of close that switch and we have a little bit of current, but it goes away. And then we open the switch and we have a little bit of current, but it's going in the other direction. And so that's electromagnetic induction. But what he wondered is, why is it only occurring right when I close the switch? So to understand that, you really have to understand the specifics of electromagnetic induction. And to understand that, you have to understand what magnetic flux is. Magnetic flux is how a conducting material, or any material for that matter, is affected by a magnetic field. And so what would be something similar? It'd be how you, or any material on our planet, is affected by light from the sun. And so it's going to be the amount of light from the sun, but it's also going to be the angle at which that light hits. And so magnetic flux is going to be the product of the strength of the magnetic field, how much or how large that magnetic field is, and then we're going to multiply that times the surface area perpendicular to that magnetic field. And so imagine that this right down here is a wire loop, and so we've got a little bit of a wire, and then we've got a magnetic field. And so if we ever have change in that magnetic flux, then we're going to have electromagnetic induction occurring. And so what happened right when he closed that circuit? Well, the magnetic field before he closed the circuit was 0, but then he added this magnetic field. So was there change in magnetic flux? Yes. And so was there electromagnetic induction? Yes. So it created current. What would happen if we were to increase the magnetic field? So let's double the magnetic field. Well, for a moment, as we're doubling the electromagnetic field, are we getting a change in the magnetic flux? Yes. Are we getting induction? Yes. And therefore, we're going to have current in that wire. And so by varying the amount of that magnetic field, we can get induction, or we can get current in that wire. Now, what's another way we could go at that? Again, we could look at the surface area that we're impacting. And so if you think of this as a wire, all of these magnetic field lines are perpendicular to this wire, and so we're going to have a large magnetic flux. But watch what happens when I turn it at an angle. And a good way to do this is simply count the lines of the magnetic field that it's hitting. You can see there's a reduction. And so the number of lines is different, but also these are not hitting it straight on. It's not perpendicular. So we'd have to use a little bit of trigonometry to figure out what component of that magnetic field is actually perpendicular to the surface area. But did it change between those two rotations? Yes. And so was there electromagnetic induction? Yes. And so there'd be current as well. And so let's say we turn it like this. The magnetic flux is going to be 0 because none of these magnetic field lines are going to be perpendicular to the surface. But it changed between those 2 points, and so we're going to have induction and we're going to have current. So that seems a little non-intuitive, but it has real-world applications. And so the electricity that you're using right now and the microphone that I'm using right now as well use this idea of electromagnetic induction. And a great way to look at that would just be looking through a generator. And so how does a generator work? Well, in a magnetic field, what we can do is we can take these wires and we can start to rotate them. And as we rotate them, we're getting huge changes in magnetic flux. And so we're going to have huge changes in the current itself. And so if we look at the equation, magnetic flux, or phi sub B, is going to be a product of the magnetic field, how big that magnetic field is, times the cross-sectional area perpendicular to that magnetic field. And so if I take this wire right here and I compare it to this wire right here, which one is going to have a larger magnetic flux? It's going to be the one on the left. And the reason why is we're going to have more of those magnetic field lines go through it. What's a good way that we could increase magnetic flux is we could just wrap that wire a bunch. And so each of those wires, we're going to have the magnetic flux of that individual wire. And so by changing the magnetic field or by changing the size of that area, we can change magnetic flux. But also remember, we could angle it. And so if I angle it like this, we're going to have fewer of those magnetic field lines go through it. And so we're going to get a change in the magnetic flux. And here we would have actually no magnetic flux. But it's not a measure of magnetic flux that's important in producing current. It's, are we getting changes over time? And so this is a PHET simulation that gets at that. And so we've got a magnet over on the left side, and then on the right side we've simply got a wire hooked up to a galvanometer, or it's a voltmeter. It's going to measure the amount of voltage. And you can see that there's no current right now, but as I start to change that position of the magnet, I'm starting to get current. And you can even see the electrons moving in the wire. And so if I increase the number of wires, I can increase how much I'm deflecting that needle, how much current I'm actually moving inside the wire itself. Why is that? Now the magnetic field lines, you can see the magnetic field lines are changing. And as they change, we're getting change in magnetic flux, and so we're getting current inside the wire. Now another way to look at this would be through a generator. And so in this setup what I have is a magnet down here on a wheel so that I can spin that magnet. I have my wire again, and I'm trying to induce current inside that wire, and then I'm going to measure the amount that I'm going to change. And so watch what happens now when I start to turn on the water inside that faucet. It's changing the position of the magnet. As it changes the position of the magnet, it changes the magnetic field. You can see the magnetic field lines are changing, and so I'm starting to get a little bit of current. What happens if I increase the speed of that water? I'm getting more current. We could even have a light bulb connected to it, and so now I'm starting to get usable energy. Watch what happens as I increase the number of wires. I even have more energy coming out, and now if I increase the water again, I even have more energy being produced. And so we're taking that energy of the flow of the water and actually making electromagnetic energy out of it. And so this is how the generators in a dam would work. We have the water flowing down through the dam, it's spinning these magnets, and it's creating that electricity. And so did you learn to construct an explanation for how a simple electromagnetic device like a generator works? I hope so, and I hope that was helpful.
ஆகவே எலக்ட்ரோமேக்னெட்டிக் இண்டக்ஷன்ற இந்த சாப்டர்ல நம்ம படிக்க போறது மேக்னெட்டிக் ஃப்ளக்ஸ்னா என்ன, இந்த மேக்னெட்டிக் ஃப்ளக்ஸ் என்னென்ன ஃபேக்டர் டிபெண்ட் பண்ணி இருக்கும், இந்த மேக்னெட்டிக் ஃப்ளக்ஸ் சேஞ்சுக்கு இஎம்எஃப்னு பேரு, ரேட் ஆஃப் சேஞ்ச் ஆஃப் மேக்னெட்டிக் ஃப்ளக்ஸ் இஸ் கால்டு இஎம்எஃப். அப்போ அந்த ஃப்ளக்ஸ் சேஞ்ச் பண்றதுக்கு 3 மெத்தட். ஃபீல்டை சேஞ்ச் பண்ணலாம், ஏரியாவை சேஞ்ச் பண்ணலாம், ஓரியன்டேஷன் சேஞ்ச் பண்ணலாம். இதை வச்சு கன்ஸ்ட்ரக்ட் பண்ணக்கூடிய இன்ஸ்ட்ருமெண்ட்ஸ், ஏசி ஜெனரேட்டர்ஸ், டிசி ஜெனரேட்டர்ஸ், இதை பத்தியும், இதுல உருவாகக்கூடிய எடி கரண்ட் அப்படின்றத பத்தியும், டிரான்ஸ்ஃபார்மர் அப்படின்றத பத்தியும், செல்ஃப் இண்டக்டன்ஸ், மியூச்சுவல் இண்டக்டன்ஸ் அப்படின்றத பத்தியும் இந்த சாப்டர் படிக்குது. இப்போ நீங்க முதல்ல இந்த வீடியோல என்ன தெரிஞ்சுக்கிட்டீங்கன்னா, ஓவரால் வியூ ஆஃப் எலக்ட்ரோமேக்னெட்டிக் இண்டக்ஷனை தெரிஞ்சுக்கிட்டீங்க. என்ன புரிஞ்சுக்கிட்டோம் அப்படின்னாக்க, ஒரு மேக்னெட்டிக் ஃப்ளக்ஸை சேஞ்ச் பண்ணா அந்த சேஞ்ச் பண்றப்போ ஒரு இஎம்எஃப் ப்ரொடியூஸ் ஆகும். அந்த இஎம்எஃப் என்ன செய்யும்னாக்க கரண்ட் அப்படின்றத யூஸ்ஃபுல்லா கொடுக்கும். இப்போ நம்ம யூடியூப் சேனல்ல நம்ம எய்ம் நீட் தமிழ்நாடு மாணவர்களுக்கு உலகம் முழுக்க இருக்கக்கூடிய மிகச்சிறந்த அறிவியல் அறிஞர்களை கொண்டு அந்த பாடப்பொருளை விளக்குவது. இதுல செமிகண்டக்டர் பிசிக்ஸ்ல எஸ்.சி. வர்மாவை இன்ட்ரடியூஸ் பண்ணோம். இப்போ ஒரு நபரை இன்ட்ரடியூஸ் பண்ண போறோம். ஒரு இன்னோவேட்டிவ் பிசிக்ஸ் டீச்சர் இந்த வேர்ல்ட், உலகம் முழுக்க வியந்து பாராட்டக்கூடிய ஒரு இயற்பியல் ஆசிரியர். பார்க்கலாமா?
The only good news is that conceptually it's not going to become more difficult. Remember that Ørsted in 1819 discovered that a steady current produces a steady magnetic field, and that connected electricity with magnetism. A little later, Faraday therefore suggested that maybe a steady magnetic field produces a steady current. And he did many experiments to show that. It turned out not to be so. And one way he tried that is as followed. He had here a battery with a switch, and here he had a solenoid. He closes the switch, a current will flow, and that creates a magnetic field in the solenoid. And that magnetic field, maybe it runs like so. Depends on the direction of the current. And so now, he put around this solenoid a loop. Let's call this loop number 2. That was around the solenoid. And let's call this loop number 1, of which the solenoid is part. Whenever there was a current in number 1, he never managed to see a current in number 2. If there is a current going in number 1, there is a magnetic field. And that magnetic field is seen, of course, by the conductor number 2, by that loop. Never any current. And so he concluded that a steady magnetic field, as produced by the solenoid, circuit 1, does not produce a steady current in number 2. But then one day, he noticed that as he closed the switch, he saw a current in number 2. And when he opened the switch, again he saw a current in number 2. And therefore he now concluded that a changing magnetic field is causing a current. Not a steady magnetic field, but a changing magnetic field. And this was a profound discovery which changed our world, and it contributed largely to the technological revolution of the late 19th and early 20th century. A current, therefore an electric field, can be produced by a changing magnetic field. And that phenomenon is called electromagnetic induction. And that phenomenon runs our economy, as you will see in the next few lectures. I have here a conducting wire, square. I could have chosen any other shape. I try to make you see three-dimensionally. And I approach this conducting wire with a bar magnet. The bar magnet has a magnetic field running like so. As I approach that loop, that conducting wire, moving the bar magnet, that's essential. I can't hold it still, I have to move it. If I come down from above and I move it down, you're going to see a current going through this loop. And that current will go into such a direction that it opposes the change of the magnetic field. The magnetic field is in down direction and it is increasing as I move the bar magnet in. Then this current loop will produce a magnetic field which is in this direction. And when you look from below, the current will go clockwise, producing a magnetic field in this direction. If you move the bar magnet out, then the magnetic field is going down here, then the current will reverse. The current wants to oppose the change in the magnetic field. And that's called Lenz Law. It is the most human law in physics, because there's inertia in all of us. We all fight change at some level. Lenz's law is extremely powerful in always determining in which direction these induced currents will run. It is not a quantitative law. You cannot calculate how strong the current will be. But it's very useful, as you will see today, to know the direction of that current. That gets you out of all kinds of problems with minus signs. I now want to do a demonstration which is very much like what you see here. I have here a loop. That is the square that you see there, except that it's not one loop, but it is many of them. Hundreds, doesn't matter. And what we're going to show you is an ammeter that is connected. So there is somewhere in this circuit an ammeter. I have a bar magnet, and I'm going to approach this conducting loop with the bar magnet. And you're going to see a current running in one direction, and when I pull it out, it will be running in the opposite direction. And when I hold my hand still, so that the magnetic field is not changing, no current. You're going to see the current meter there. And here is my bar magnet. I come close to this conducting loop. Notice, you see a current. I pull back, current is in the other direction. Now I will go faster, so that the change of the magnetic field per unit time is stronger. More current. I go out fast, more current. So you see, it's the change of the magnetic field that matters. If I come in very slowly, which I do now, very slowly, you almost see nothing. And right now, the entire magnetic field is inside this loop. The strongest I can have it. Nothing happens because there is no change in the magnetic field. It's only when I do this that you see the current. So an induced current is clearly the result of a driving force. There must be, just like we had with batteries in the past, there must be an EMF. There must be an electric field that is produced in this conducting loop. And so I create now an induced EMF. We used that word EMF earlier for batteries. So now we have an induced EMF, which is the result of this changing magnetic field. And that, therefore, is the induced current times the resistance of that entire closed conductor, whatever is in there. In this case, the total resistance of all these windings, of all the copper wire. That's Ohm's law. So the induced EMF is always the induced current times the resistance. Faraday did a lot of experiments. And one of the experiments that he did was that he produced a magnetic field. So he ran a current through a loop of some kind. Let's say he ran a current going around, creating therefore a magnetic field. And he was switching the current in and out so that he could change the current. And so it produces a magnetic field. And this magnetic field changes when you close and open the switch. And then here, he had his second conducting wire, just like we had there, and he measured in there the current. And what he found experimentally is that the EMF that is generated in here, which I will call EMF generated in my conducting loop number 2, is proportional to the magnetic field change produced by number 1. So the field goes through number 2, and this field is changing. So he noticed that if the change is faster, as you just saw, you get a higher EMF. He also noticed that E2 is proportional to this area, so to the area of number 2. And that gave him the idea that the EMF really is the result of the change of the magnetic flux through this surface of number 2. And I want to refresh your memory on the idea of magnetic flux. We do know, or we remember what electric flux is. And magnetic flux is very similar. If this is a surface, and the local vector perpendicular to the surface is like so, of course it could be in a different direction, and the local magnetic field is, for instance, like so, then the magnetic flux through this surface is defined, we call it phi of B, is the integral over an open surface. This is an open surface of B dot dA. An electric field, we defined in exactly the same way, electric flux, except we had an E here. There was nothing there. So if this magnetic flux is changing, Faraday concluded that then you have an EMF in this conducting wire. So essential is the change of the magnetic flux. If we take some kind of a conducting wire, like so, let's make it in the blackboard for now to make it easy. And I attach to this wire a surface, because the moment that you talk about flux, you must always specify your surface. A flux can only go through a surface. So this is my surface now, for simplicity. And there is a magnetic field coming out of the blackboard at me, and it is growing. It is increasing. I will now get an EMF, a current, flowing in this direction. Lenz Law. If the magnetic field is increasing, then the current will be in such a direction that it opposes the change. It doesn't want that magnetic field to increase, and so it goes around like this, the current, so that it produces a magnetic field that is in the blackboard. And so it is the flux change of that magnetic field through this flat surface that determines the EMF. So the EMF is then the flux change d phi dt through that surface. To express Lenz law that it is always opposing the change of the magnetic flux, we have a minus sign here. That minus sign will never bother you, believe me, because you always know in which direction the EMF is. It's clear that the EMF is going to be in this direction. That's the direction in which it will make the current flow. But we have to put it there to be mathematically correct. That's really Lenz law. You're looking at Lenz law here. So you can also write down for this minus the surface integral of B dot dA over that open, I hope you didn't see this, over this open surface. That's the same thing. Oops, look what I did. I forgot the ddt in front of the integral sign. Sorry for that. If you put yourself inside that conductor and you march around in the direction of the current, you will see everywhere in the wire an electric field, of course, otherwise there would be no current flowing. And so if you go once around this whole circuit, then that EMF must, of course, also be E dot dl over the closed loop. So you're marching inside the wire, you find everywhere an electric field, and these little sections are dl. E and dl are always in the same direction if you stay in the wire, and so this should be the same, and this is a closed loop. So this is all, if you want, what we call Faraday's law. We never see it in so much detail. I will abbreviate it a little bit on the board there, but I want you to appreciate that there is no battery in this circuit. There is only a change in the magnetic flux through a surface that I have attached to the conducting wire. And then I get an induced EMF, and the induced EMF will produce a current given by Ohm's law. So I want to write down now on that blackboard there Faraday's law in a somewhat abbreviated way, because we have all Maxwell's equations here. And so we now have that the closed loop integral, closed loop of E dot dl, that's that induced EMF. You can take minus d phi dt, or the time derivative of the integral B dot dA. That's the one I will take. Integral of B dot dA, and this is over an open surface. And that open surface has to be attached to this loop. And that is Faraday. We had Gauss' law. We have Ampere's law. We have this one, which tells you that magnetic monopoles don't exist. This would only not be zero if you had a magnetic monopole and put it in a closed surface. Come and see me if you find one. And this now is Faraday's law. So you think that all four Maxwell's equations are now complete. Not quite. We're going to change this one shortly. So we can't celebrate yet. We have to wait. It's the big party. There's always a little bit of an issue about the direction of dA. And I will explain to you how the convention goes, but it really is not so crucial because Lenz law always helps you to find the direction of the EMF. But if we are trying to be a purist, if this is my conducting loop, and if I attach a flat surface to this, if I did that, and if I go around the closed loop integral E dot dl, Faraday doesn't tell me which way I have to go. I can go clockwise, I can go counterclockwise. We will then do the same thing that we did before with Ampere's law, apply the right-hand corkscrew rule, and that is that if you march around clockwise, then dA will be in the blackboard, perpendicular to the blackboard, perpendicular to this surface, and if you go counterclockwise, then dA will come towards you. The surface doesn't have to be flat. It can be flat, there's nothing wrong with it, but there can also be a bag attached to it. As we also had earlier, I have here a closed conducting wire, and I could put a surface right here, but I can also make it a head, like this, perfectly fine. Nothing wrong with that. That's an open surface attached to this loop. That's fine. You have a choice. And the convention with dA is then exactly the same, that if you go clockwise, then the dA would be in this direction. Using the right-hand corkscrew, locally here, if you went counterclockwise, the dA would flip over. So what is now the recipe that you have to follow? You have a circuit, electric circuit, that determines then your loops, of course. You can take loops anywhere in space, but that's not too meaningful. So you take them into your circuits, and so you define the loop first. Then you define the direction in which you want to march around that circuit. You attach an open surface to that closed loop, and you can determine on that entire surface the integral of B dot dA. Everywhere on that surface, locally you know the dA, locally you know the B, you do the integration and you get your magnetic flux. And then if you know the time change of that magnetic flux, then you know the EMF. If you go around in this conducting circuit and you measure everywhere the electric field, then the integral of E dot dl, if you go around the loop, will give you the same answer. And that connects the two. The magnetic flux change is connected with the integral of E dot dl when you go around. You have to take that minus sign into account. How come it doesn't matter whether you choose a flat surface or whether you choose a bag? Well, think of magnetic field lines as a flow of water or spaghetti, if you like that, or a flow of air. It is clear that if there is some kind of a flow of air through this opening, then it's got to come out somewhere, so it always comes out of this surface. And therefore, you're really free to choose that surface. So you always pick a surface that is the best one for you. Now all this looks very complicated, but in practice it really isn't. Because your loop is always a conducting wire in your circuit. And the minus sign is never an issue because you always know with Lenz Law in which direction the EMF is. In fact, when I solve these problems, I don't even look at the minus sign. I ignore it completely. I calculate the magnetic flux change, and then I always know in which direction the current is. So I don't even look at the minus sign. Now I want to show you a demonstration which is very much like what Faraday tried to do. I have here a solenoid. We've seen this one before. We can generate quite a strong magnetic field with that. And we're going to put around this solenoid one loop, like we had here, like Faraday did. And then we're going to close the switch. And so we're going to build up this magnetic field, and we're going to see the current in that loop. And so if we make a cross-section straight through here, then it will look as follows. Then you see here the solenoid. So the magnetic field is really confined to the solenoid. Magnetic field outside the solenoid, as we discussed earlier, is almost zero. So there's only a magnetic field right here. Keep that in mind in what follows. And now we're going to put a wire around it with an ammeter in there. If the magnetic field comes out of the board and is growing, is increasing, the current will flow in this direction. Lenz Law. If it is decreasing, the current will go in the opposite direction. Now keep in mind that the magnetic flux through this surface, that is my surface which I attach to this closed loop, that magnetic flux remains the same whether I make the loop this big or whether I make the loop very crooked, like so, because the magnetic flux is only confined to the inner portion of the solenoid, and that's not changing. And so when I change the shape of this outer loop, you will not see any change in the current. I hope that doesn't confuse you. I'm going to purposely change the size of the loop. And so I'm going to do that now. You're going to see there a very sensitive ammeter. And you're going to see here this loop, the big wire, and I'm going to just put it over this solenoid. Let me first make sure that my ammeter, which is extremely sensitive, I can zero it. It's sign sensitive. If the current goes in one direction, you will see the needle go in one direction. If the current goes in the other direction, you will see the change. And so now I put this loop around here. Crazy shape, this loop. So it's around this solenoid once. So the magnetic field is inside the solenoid. And so think of a surface which is attached to this crazy loop. And now I'm going to turn the current on, and only while the current is changing will there be a changing magnetic flux. Only during that portion will you see a current flow. 3, 2, 1, 0. I will break the current. 3, 2, 1, 0. Went the other direction. If I change the size of the loop, I'm making it now different. Much smaller makes no difference for reasons that I explained to you, because the magnetic flux is not determined in this case by the size of my loop, but is determined by the solenoid. So if I do it again now, with a very different shape of the loop, let me zero this again. 3, 2, 1, 0. 3, 2, 1, 0. No change. Almost the same what you saw before. Now comes something that may not be so intuitive to you. I'm now going to wrap this wire 3 times around. And so this outer loop, this outer conducting wire, is now like this. 1, 2, 3. Something like that. Now I have to attach in my head a surface to this closed loop. My God, what does it look like? What a ridiculous surface. Well, that's your problem, not Faraday's problem. How can you imagine that there is a surface attached to this loop? Well, take the whole thing and dip it in soap. Take it out and see what you see. The soap will attach everywhere on the conducting loop. And if this loop were like this, going up like a spiral staircase, you're going to get a surface that goes up like this. But the magnetic fields go through all three of them. Therefore, the changing magnetic flux will go 3 times through the surface now. And so Faraday says, fine, then you're going to see 3 times the EMF that you would see if there were only one loop. And if you go 1,000 times around, you get 1,000 times the EMF of one loop. Not so intuitive. So, I'm around now once, I go around twice, and I go around the 3rd time. I have 3 loops around it now. I can zero that, but that's not so important. 3, 2, 1, 0. You saw a much larger current. It's about 3 times larger because the EMF is 3 times larger. I break the current, and you see it 3 times larger. And this is the idea behind transformers. You can get any EMF in that wire that you want to by having many, many loops. You can get it up to thousands of volts. And that's not so intuitive. So Faraday's law is very non-intuitive. Kirchhoff's rule was very intuitive. Kirchhoff said when you go around a circuit, the closed loop integral of E dot dl is always 0. Not true if you have a changing magnetic flux. If you have a changing magnetic flux, the electric fields inside the conducting wires now become non-conservative. Kirchhoff's rule only holds as long as the electric fields are conservative. If an electric field is conservative and you go from point 1 to point 2, the integral E dot dl is independent of the path. That's the potential difference between 2 points. That's uniquely defined. That's no longer the case. If you go around once with this experiment, you get a certain EMF. You go 3 times around, you get a different value. Your path is now different. And that's very non-intuitive, because you're dealing with non-conservative fields, for which we have very little feeling. Now, I'm going to blow your mind. I'm going to make you see something that you won't believe. And so try to follow step by step, leading up to this unbelievable and very non-intuitive result. I have here a battery, and the battery has an EMF of 1 volt. Here is a resistor, R1, which is 100 ohms. And here is a resistor, R2, which is 900 ohms. And I'm asking you, what is the current that is flowing around? And you will laugh at me. You will say, that's almost an insult. I wish you had given that problem at the first exam. Because E equals the current that is going to run divided by R1 plus R2. Oh my goodness, what did I do? I forgot Ohm's law. E equals IR, remember? Not I over R. So R1 plus R2 should go upstairs. And everything that follows is correct, so you don't have to worry about that. This was just a big slip of the pen. And so the current I is 10 to the minus 3 amperes. 1 milliampere. Big deal. Easy. Current is going to flow like this. Fine. Let's call this point D, and we call this point A. And I asked you, what is the potential difference between D and A? You will be equally insulted. VD minus VA. You apply Ohm's law. You say that's this current times R2. Absolutely. I times R2. So that is plus 0.9 volts. Now I say to you, well, suppose you had gone this way, then you would have said, well, I find the same thing, of course. Kirchhoff's rule. So indeed, if you go VD minus VA, and you go this way, then notice this battery, this point is 1 volt above this point. But you have in the resistor here, you have a voltage drop, according to Ohm's law. And the current times 100 ohms gives you a 1/10 voltage drop here. So VD minus VA is the 1 volt from the battery minus I times R1, and that is plus 0.9 volts. What a waste of time that we did it twice and we found the same result. So I connect here a voltmeter. The voltmeter is connected to point D and to point A. And I ask you, what are you going to see? The answer is plus 0.9 volts. And you will, provided that the plus side of the voltmeter is connected here and the minus side of the voltmeter there. Voltmeters are polarity sensitive. This is fine. Kirchhoff rule works. The closed loop integral from E dot dl going from D back to D is 0. So far, so good. Now, hold on to your chairs. I'm going to take the battery out. Who needs the battery? I'm going to replace the battery by a solenoid, which you see right here. And this solenoid, when I switch it on, is creating an increasing magnetic field, only here. And let's assume that that increasing magnetic field is coming out of the board, and that it is increasing. Lenz Law will immediately tell you in what direction the current is. If this magnetic field is increasing towards you, the current will be in this direction. The magnetic flux change, d phi dt, at a particular moment in time, happens to be 1 volt. An amazing coincidence, isn't it? E induced at the moment in time is 1 volt. So now, I ask you, what is the current? Well, you'll be surprised that I even have the courage to ask you that, because Ohm's law holds. The induced EMF is 1 volt, and R1 plus R2 is still 1000 ohms, so 10 to the minus 3 amperes. I really make a nuisance of myself and I say, what is VD minus VA? And you get annoyed at me and you say, look, the current I through R2, Ohm's law, V equals IR plus 0.9 volts. And then I say, but now suppose we go the other side, and we want to know now what VD minus VA is. And now, it's not so simple, because there's no battery. And so now, when I go from D to A, I don't have this 1. And therefore, I now find minus 0.1 volts. I find a totally different answer. I attach a voltmeter here. That voltmeter will show me plus 0.9 volts. Now I attach a voltmeter here. The same one. I flip it over. It's connected between point D and point A. It will read minus 0.1 volts. This voltmeter, which is connected between D and A, reads plus 0.9. This voltmeter, which is connected to D and A, reads minus 0.1. The two values are different. And I placed on the web a lecture supplement which goes through the derivation step by step, which will convince you that indeed this is what is happening. Why we can't digest this so easily is we don't know how to handle non-conservative fields. If you have a non-conservative field, then if you go from A to D of E dot dl, or from D to A for that matter, it doesn't matter, the answer depends on the path. It's no longer independent of the path. And so, if here is D and here is A, and you go this way, you find 0.9 volts plus. If you go this way, you find minus 0.1 volts. Faraday has no problems with that. Kirchhoff has a problem with that. But who cares about Kirchhoff? Faraday is the law that matters. Because Faraday's law always holds. Because if the phi dt is 0, then you get Kirchhoff's. Kirchhoff's rule is simply a special case of Faraday's law. And Faraday's law always holds. So Kirchhoff is for the birds, and Faraday is not. Suppose you go from D to A and back to D. Well, we know that Vd minus Va, if we go through this, if we go this way through R2, we know that Vd minus Va is plus 0.9 volts. Now we are at A, and we go through the left side back to D. So we now have Va minus Vd. That, of course, is now plus 0.1 volts, because remember, if Vd minus Va is minus 0.1, then Va minus Vd is plus. And so we add them up, and we find that Vd minus Vd is plus 1 volt. Kirchhoff said, has to be 0, because I'm back at the same potential where I was before. Faraday says, I'm sorry, you can't do that. That 1 volt is exactly that EMF of 1 volt. That is the closed loop integral of E dot dl around that loop. It's no longer 0. And therefore, whenever you define potential difference, if you do that in the way of the integral of E dot dl, keep in mind that with non-conservative fields, it depends on the path, and that is very non-intuitive. And I'm going to demonstrate this now to you. I have a circuit which is exactly what you have here. I have 900 ohms in a conducting copper wire here, and I have 100 ohms here, and here is the solenoid. And we can switch the current on in the solenoid and get a blast of magnetic field coming up, and the system is going to react by driving a current in the direction that you see there. And I'd like to be even a little bit more quantitative so that you get a little bit more for your money. The magnetic field takes a little bit of time to reach the maximum value. In this course, we will be able to calculate the time that it takes for the magnetic field to build up. We didn't get to that yet, so forget that part. It's not so important. I just want you to appreciate the fact that the magnetic field, as a function of time, will come up like this and will then reach a maximum. It's no longer changing. It's constant. It's a maximum value. It's very high. It's 700-800 Gauss or so for this unit. We are not interested in the magnetic field. We're interested in the change of the magnetic field. So the change of the magnetic field, dB dt, is going to be something like this. So it's the derivative of this curve. And that is proportional with the induced EMF, and that's proportional with the current through Ohm's law. So if we now plot the voltage as a function of, let me do that here, the voltage as a function of time, then that voltmeter on the right side, I call that V2, will do this. This is V2, which is I times R2. At the maximum value, if those values were correct, it would be 0.9 volts. And V1 will go like this. V1 equals minus I times R1. That gives me the minus 0.1 volts. So the question now is, what is the largest value of the BDT that we can expect? We also have to know the surface area of the solenoid, so we can convert it to a flux change. Well, the change in magnetic field is roughly at the fastest here is about 100 Gauss in 1 millisecond. Very roughly. So that would mean a field change, the BDT, that's the maximum value possible only in the beginning, of about 10 Tesla per second. And the surface area, which is that inner circle there through which the flux is changing, the fact that my surface has to be attached to that loop doesn't change the magnetic flux. The magnetic flux is only determined, of course, by that inner portion. And so if the inner portion has an area of, say, 10 square centimeters, which is 10 to the minus 2 square meters, then the phi dt will be approximately 10 times 10 to the minus 2, so that's about 0.1, and that's volts. That's EMF. I don't care about the direction because I know Lenz Law. So you're going to see an experiment which is almost identical to what I have there, except all values are down by a factor of 10. But that's all. And you're going to see that demonstration there. And a few years ago, when I first did this experiment in 26100, there were several of my colleagues, professors of both the physics department and the E department, in my audience. And some did not believe what they saw. In fact, it was so bad that after my lecture, they came to me and some accused me for having cheated on the demonstration. This tells you something about them. Imagine professors in physics and professors in electrical engineering department who did not believe what they were seeing. That tells you how non-intuitive this is. The simple fact that we had one voltmeter connected to point D and A and another voltmeter connected to the same point, they were unwilling to accept that the two voltmeters read a totally different value. They were not used to non-conservative fields. Their brains couldn't handle it. But that's the way it is. And I'm going to show this to you now. You're going to see it there. And when you see this demonstration, it will be probably the only time in your life that you will ever see this. And I want you to remember this. You're going to see something that is very strange, and I want you to tell your grandchildren about it. That you have actually seen it with your own eyes. You're going to see it there. On the left side, you're going to see V1, and on the right side, you're going to see V2. The vertical scale is such that very roughly, from here to here is about 0.1 volts. And a horizontal unit is about 5 milliseconds. And the whole voltage pulse lasts about 10 milliseconds, because from here to here is about 10 milliseconds. And the value that you expect for V2 will be 9 times higher than V1, and the polarities will be reversed. If you're ready for this big moment in your life, 3, 2, 1, 0. Look on the left, there's V1. Notice, it's negative. Look on the right, there's V2. It's about 9 times larger than V1. Don't pay any attention to this wiggle that has to do with the voltage that we apply, which is not exactly flat. And notice that the whole pulse goes from here to here, lasts about 10.
சாதாரணமா இருக்கக்கூடிய ஃபேரடேஸ் எக்ஸ்பெரிமெண்ட்டை லென்ஸ் லா வச்சுட்டு அன்பிலீவபிள் திங்ஸ் ஃபார் நான் கன்சர்வேட்டிவ் ஃபீல்டுக்கு டெமோ பண்ணதை பார்த்துருப்பீங்க. தட் இஸ் பிசிக்ஸ். தொடர்ந்து பாருங்க.